So we have here a simply supported beam, but in this instance, the reaction forces that we are going to calculate, they are not located at the end of the beam. And this seemed to be a major issue for some students. So I'm going to go through this in a step-by-step method. Now, the first thing that we need to notice, of course, is that our reaction forces, R1 and R2, they are not located at the edge of the beam. But our process will remain the same. We just have to be a lot more careful when we're evaluating the forces and their impacts. So to begin with, we're going to set up our same system of equation and we're going to analyze these forces. So we do know that the sum of the moments, and in this instance, we're going to go about R1. So that's going to be our pivot point, and the sum of the moments should equal to 0, 0. Now, it's quite useful to set up your clockwise moment to be equal to your counterclockwise moment, just as we did before. And what we're going to do now is to determine the direction that these forces will be trying to pivot or rotate the system. So if we start with the 7 kilonewtons to the left of R1, it's safe to say that that force will be trying to rotate in that direction, which is going counterclockwise. Then when we go across to that 15 kilonewtons, that will be trying to go in the opposite direction like that. The 9 kilonewtons as well will be trying to go in the same direction as the 15 kilonewtons. And then our R2 will be trying to pivot in the opposite direction. So in this instance, we have two forces that are trying to go clockwise and two that's trying to go counterclockwise. So the only thing that we need to figure out now is what we are using as our distances. So I'm going to start with the clockwise moment first. So that would be my 15 kilonewtons. So that's 15. And that will be multiplied by our distance here from R1, which is 3 meters. So 15 times 3. And I'm going to sum all the clockwise rotations first. So next I'll go to that 9 kilonewtons. And that 9 kilonewtons, its distance from our same point there, R1, will be that 3 meters plus that next 5 meters. So that's going to be 8 meters there. And then if we go across now to our counterclockwise moment, then we have that 7 kilonewtons, and we are looking at the distance of the 7 kilonewtons there from R1. And if you look to the left, you'll notice that it's that 2 meters right there. So what we have is 7 times 2 for that one. And R2, its distance from R1 down here, you can see that 7 meters. So R2 in this equation will be our unknown. So what we have here is plus 7 times R2. And all we have to do now is just to solve this equation. So 15 times 3, that's our 45 plus 72. And that will be equal to 14 plus 7 times R2. So let's just simplify a bit further before we solve for R2. So that will be 117. That equals 14 plus 7 R2. So now we can just go ahead and get what R2 equals. And if we do inverse operations here, then that will just simply be 117 minus our 14 and all divided by 7. So we get the value of R2 now, and that will give us 14.71, and that's kilonewtons. So that gives us our R2, and all we have to do now is apply our next equilibrium equation to get what R1 is. And all that is, we're just going to say that the forces going up should be equal to the forces going downwards. So if we sum all the forces going upwards, then that will just be R1 plus R2. And if we sum all the forces going downwards, then that will just be 7 plus our 15 and plus our 9. So we already know what R2 is, so we can just go ahead and solve for R1. So R1 is equal to our 7 plus 15 and plus 9, and take away what we just got for R2, which is 14.71. So we get a final answer for R1 as 16.29, and that's kilonewtons there again. So that's it. We have found both reactions, but if you don't understand how to do this when we have a UDL force, then you should check out these two videos where I go through that example step by step.